Hello guys. So today I would like to talk to you about an active overvoltage protection. On YouTube I saw many videos about overvoltage protection, but none of them spoke about power electronics overvoltage protection. So nobody said what you should do if you have something like 1 kilovolt and at some point it goes to 1.2 kilovolt, something like this. Or even the output voltage, or I don't know, even for a PFC, like you have 380 volts after the PFC output. What if this guy goes from 380 volts to, I don't know, 420 volts for some reason? So let's start first from the lowest part of the overvoltage protection. So when you have the auxiliary power supplies, okay, which can be bucks, can be flybacks, or can be even LDO, or can be even an PNP transistor. And auxiliary power supplies are in the range of low power, less than 50 watts. Most of the time, these guys are just IC, and you do have only to put the transformer or the inductor outside. That is more or less what they should do. For this kind of guys, you can just use simply a Zener diode, and it will be most of the time will be sufficient. If you decide to use a PNP instead, then a famous circuit can come in handy. You do have your power supply, and then you bias a Zener diode, you connect it with a PNP transistor, like this. Ah yes, don't forget to put a resistor here. And you do have your series PNP. This is basically your circuit. Now, this block here basically is the OVP. This guy set the reference. And this one is the DUT, is the PNP, is the guy who is protected by the overvoltage protection. And this one is the load. And be careful that this circuit can be only used in low power ranges, only when you have to, in fact, as I said before, just for auxiliary power supplies and not more. Later we will see how you can deal with overvoltage protection when you have, for instance, a 10 kilowatt buck converter, a multi-phase 3 kilowatt buck converter, whatever they are. That is, in my opinion, more useful than this. So first let's simulate this guy and let's see how it works. This is my first part of the video. So let's deal first with the auxiliary power supplies. So let's open LTSPICE and let's put our voltage, which in this case will be a ramp between 0 and 100. I don't care, honestly. Rise time 10 milli and fall time 1 nano. T on 1, period 2, we don't care. We just want to put a ramp between 0 and 100. We just don't care about whatever that it is. So if you run this guy for 1 second, you will see that it is just a ramp. Okay, we just need for the milli. Okay, just a ramp between 0 and 100. Okay, that's perfect. So what we want to do now, we can hide this guy. We know that is just a ramp. Okay, ramp 0 100. Then we have to put first our diode here, where you can bias it with just 1 kilo. We don't care actually. So let's put a random, really random Zener diode. Breakdown 20 volts. Yes. Now you can even just simulate this guy, and you can see that it is clamping at 20 volts. Yeah, that's how a Zener diode works. you know. Problem is that the more voltage you give the guy, you give the guy, the more current it has to sink. So pay attention to the dissipation, because this guy is dissipating 2 watts. And I'm not sure that this guy can handle it. So pay attention. Ah, now it's better. Definitely better. So we want to make a protection. So when this guy, so the circuit works like this. What is the key of the circuit? And I want you to really understand. When you reach 20 volts, the base, this guy will be active. Sorry. Let's explain in a better way. But to do that, I need you to. Yes, it's better if I connect these 2 guys like this, so that you can now that you can understand. So basically, now why I want to stop now, because the point of this circuit is to activate this transistor so that this part, the base and the emitter, are shorted of the guy. And he has no way, since it is a PNP, he has no way to actually conduct. So that's why I wanted to block the circuit now, because now you can understand what's going on. You have 20 volt here. When you have a PNP, the base, or also a PMOS, is the same. It is the contrary. Okay. When you have an NPN, the base has always to be higher than its emitter. Okay. The emitter, if the emitter is to 0 and this guy is polarized with, I don't know, 3 volts and a resistor, you know that you will see 0.7 across it. Also in an NMOS is the same. When you have 5 volts here and 0 volt here, it conducts. Okay, but when you use the counterpart, I mean when you use the PNP or the PMOS, it's the same. A PMOS, in order to conduct, the gate has to be lower than its emitter. Okay, so remember this mechanism in mind. Select just one PNP randomly for the list. Don't forget to put a resistor to ground to create a path. And let's put a load of, don't know, 1 kilo. We don't care. So now you can understand what's going on. Basically, the voltage is clamped to 20 volts as we expected. And now let's see each node. So this one is B1. And this one is E, because it's the emitter for both of them. And the collector, we don't need that. Now, run again. Check between the base and the meter. Meter base, sorry. It's the contrary. Of course, when you have a PNP transistor, you don't study the VBE, but you study the VAB, okay? Because it's a contrary. So basically what we see is that for the first 2 milliseconds, the VAB is 0, because it has not reached yet the point of clamping, meaning that in this point the circuit is working correctly. And to prove this, we just see how much current is flowing. As we can see, the current is flowing into the load. And the VAB is 0. Now, what happens when you have actually a voltage here? The VAB rises. When you exceed the overvoltage, the VAB rises from 0.8 to, let me study with this, it's more convenient. From 0.8 onwards it rises, so this guy is active. Oops. So this guy is active, and once this guy is active, the emitter and the base are gone. So this guy is basically not existent, and your load is protected. You can also verify this by putting the VAB of the other guy. As you can see, the VAB of this transistor goes to 0. Okay? While this is rising because this transistor is active, this transistor goes to 0. Because when Q1 is active, it performs a short circuit. Well, not exactly a short circuit because there is a drop of is VEC, and as you can see here, it does not go to 0 perfectly, but what you see here in this point is the VCE drop, which is around 100 millivolts, 50 to 100 millivolts or something like that. And as you can see, it works, and you see the VCE drop of this, but it's enough to bring the Q2 to 0. So this is one circuit that you can use to actually protect your power supplies. But do you see how much power this guy can handle? You see? He cannot handle so much power. That's why I said, okay, you can handle just less than 50 watts with this kind of circuit. Now, let's see. Now, this is the second part of the video. And let's see what we can do. What we can do when we have a buck converter. So for now, let me save this guy with save as wait. Where's my PNP protection circuit? Don't know why the ESC file are like this, by the way. So we can close the guy, don't need it anymore. And now what we can do is how we can protect our buck converter. Now, before doing that, we have to analyze if your design, if your project relies on a microcontroller or an IC controller, because there is no way that you are designing a 10 kilowatt buck converter without a microcontroller or without an IC. There is really no way, because for a 10 kilowatt and for instance 250 kilohertz switching frequency, you have to rely on synchronous parallel phases, and you have an AC which can handle that. So most of the time you have two choices: microcontroller or IC. Now, if you have a microcontroller, then it's way easier because you can basically read the line voltage. This is your V in. You can read your line voltage like that. And inside an ADC channel, some micro of the Texas have already comparators integrated. You can immediately shut down the switching signals coming from the microcontroller. So this is way easier. You just need to put a divider. When this divider, so when let's call this VD, let's suppose that VD is equal to V in times, this is R2 and this is R1. You have R2 over R1 plus R2. When this is greater than your threshold VK, let's call like that, then you interrupt the switching. You bring to 0 basically the GPIO port to 0. They basically you interrupt the switching if the switching is generated by the port. If the microcontroller does not generate the square waveforms, then you can still use a pin to bring down a shutdown into the shutdown part of your IC. Shutdown, enable, you can bring this pin to 0 or whatever they are. So if you have a microcontroller, it's very, very, very easily, because all the logic of the overprotection or the stuff are really handled by the firmware. So you don't have to worry too much. It's very easy. Now let's see in the IC. This is pure analog. And that's what I want to talk about today. So I have to bring an IC to life. Let's see, LTC 680 can be an example. Okay, this is what? A 60 volt high frequency synchronous step down controller. Okay, let's open the microcontroller test feature. Let's close the guy. And let's run the guy for a second. Just want to see how much power it can give. Just to have an idea. Let me pick the datasheet. It's faster. LTC 680. Let's see the datasheet. So this can have okay, so this is 65 volts. It's resistance here sensing, burst mode. Yeah, can be a good example, definitely. High switching frequency, high performance step down converter. You have also this is one channel, current controlled. Yeah, this is definitely a good example. It has everything that a controller should have. Okay. So what happens if the input power grows a lot? We really want to know how to shut down this stuff. You see that these kind of controllers, they do have some pin called run, enable, shut down. So you have to act on this pin. So you want to implement a logic net that takes the output and also the input. If one of these two is higher than the threshold, then you can bring the line, you can bring the run to 0. 3 volt, 0. Because if I put 0 to the run, you see, the output voltage is no more. Because it interrupts all the logic inside. So, what we need to do is to create a sort of logic. Let's see that... No, stop. I don't need that. This was just an example. So again, I need a ramp between 0 and 100. Rise time of 10 milli. Now, we have to design our net. Pay attention. If you are working, pay attention, because if you are working with, like I said before, with 1 kilovolt, you can't put 1 kilo ohm here as a divider, because if you do that, the corresponding impedance will have a current, will make a current of 1 amp, and this is not feasible. So if you have 1 kilovolt, you have to put mega ohm. And pay attention when you select, here op amps, because the current, the leakage, his impedance has to be compared with that impedance. Okay, so be careful. But anyway, we have to design a divider. Let's put for now 1 kilo ohm, and let's put for now 3 kilo ohm and 10 kilo ohm here. And we have also to put a reference. We can put a Zener diode. Let's put... And then we have to put a DO pump. Let's make the opposite. So suppose that we want to design a threshold. We don't have to make the perfect design now. So we can just make the threshold to act on purpose. Now we want to have the universal op amp. always use level 2. And we want to bring down the run. So we have to put on the minus the reference and on the plus the minus. This is to 0 and this is to 3 volts. And now let's see. Okay, so and this is the still rising. Oh. Is there some kind of... Is there a bug or something? Should not act like this. Okay. Ah, okay. So now it's perfect. Okay, on the plus we have the input divided by this divider, and here we have just a reference, which can be done with a Zener diode, like this, or you can just put now for simulation purposes. Let's just put a constant voltage, like, don't know. It's the same, just for faster simulation. Let's put 2 volts, for instance. Okay, 2 volts here. And yeah, at a certain point is exceeding the voltage threshold. Now, we have to bring this line, and we can do the same also for the output, but for the output is a little bit different because you have the feedback and the control loop. So the control loop should also already take care of the overvoltage. But in any case, some designers prefer to also to use that and to act on the feedback or to act directly on the run. It's your choice. And now you have to connect. Let's suppose that there are also other conditions, and you have to connect the run, the output of the op-amp, like this. Now, if you do that, LTSPICE will give you an error because you are shorting a perfect ideal voltage, or something basically will not work. As you can see, the run is always to 3.3. It's not a bug. It's that LTSPICE creates a perfect, okay, voltage source. In reality, this does not happen, okay? So to simulate correctly this, you have to put a resistor of 1 kilo ohm. And there you go. Let's wait for a bit. Yeah, we have to wait. Wait, why 1 millisecond? Wait a second. I put this one on when the plus is higher than the minus. You bring the guy to up. Ah, sorry. It's true. Ah, sorry. It's the contrary. Okay, so now it works fine. After it reaches the threshold, which is in this case at 5 volts, it's just an example, guys, but understand. The run goes to 0 and it stops switching. Now we can just make the simulation a bit more realistic. We can reduce here the divider to 5K, and we will prolong a lot this. So now it's switching. The input voltage is rising, is rising, is rising. At a certain point, this guy will just bring down the run. And the switching will go down. So that's a real overvoltage protection that you can use for the input. That's a real one. Okay? And as you can see, now the waveforms are all coming together. A very, very simple circuit, but nobody talked about, and so I think that this can be the end of the video. I just leave you the meaning, the real plots. Okay, so this is, let's call these names as they should. So this is the run, and this is the input, yeah. This is the ref. And as you can see, the run pin is going down. The switching pin is also going down. And also, perfect. So you see the feedback and also the reference, and it goes down perfectly. Thank you guys for all the subscription, and see you in the next video. Bye bye.